The engine's sitting under your hood right now. Do you actually know what type it is? Most people have no idea. They just know it runs. Sometimes. And that is exactly why so many car owners end up with brutal fuel costs, endless mechanic visits, and cars that die at 50,000 miles when they should have lasted 200,000. Here is the thing. Pick the wrong engine type and you are stuck with thousands in repairs you never saw coming. Pick the right one and suddenly everything changes. Better gas mileage, less maintenance, a car that actually sounds good when you floor it. But nobody explains this stuff in a way that actually makes sense. Until now. This is every car engine type ever made, explained in one video. And by the end, you will understand exactly what is powering your car, why it matters, and what trade-offs you are really dealing with. We are going to break this down into 4 categories: fuel type, cylinder arrangement, how many cylinders, and how the engine breathes. Every engine ever made fits somewhere in these categories. Let us start with the most basic question. Before we even talk about cylinders and configurations, we need to talk about fuel, because what your engine burns changes absolutely everything about how it works. Gasoline and diesel are not just different colored liquids you put in your car. They are completely different chemicals that need completely different engines to work properly. Put diesel in a gasoline engine, and you are looking at a very expensive tow truck ride. I have seen it happen more than once. Gasoline engines use something called spark ignition, and here is how it actually works. The engine mixes fuel with air, sucks that mixture into the cylinder, compresses it down, and then boom. A tiny spark plug creates a spark that ignites everything. Explosion. Power. That's simple. Think of it like lighting a gas grill. Fuel, air, spark, fire. The key word here is spark. The engine controls exactly when combustion happens by controlling exactly when that spark fires. This is why gasoline engines tend to rev higher, sound smoother, and run quieter. They work great in smaller cars where you want quick response and a smooth ride. Most gasoline engines run compression ratios somewhere between 6:1 and 12:1. That means the engine squeezes the air and fuel mixture to about 6 to 12 times its original size before lighting it up. Squeeze it too hard, and it will literally explode before you want it to. That is called knock, and knock absolutely destroys engines over time. It is like a jackhammer going off inside your engine block. But wait, there is another fuel type that takes a completely different approach, and once you understand it, you will know exactly why diesel trucks sound the way they do. Diesel engines flip the whole thing around. They do not even use spark plugs. Instead, they use something called compression ignition. Here's what happens. The engine sucks in just air. No fuel yet. Then it compresses that air so hard it gets extremely hot. We are talking temperatures hot enough to ignite diesel fuel the moment it touches. Then the engine sprays fuel directly into that superheated air, and the fuel just ignites by itself. No spark needed at all. Think of it like using a bicycle pump. When you pump air really fast, that pump gets warm. Now imagine compressing air so hard it gets hot enough to start a fire. That is exactly what happens inside a diesel engine every single time it fires. This is why diesel engines need way higher compression ratios. We are talking 15:1 all the way up to 25:1. They literally squeeze the air so tight that it gets hot enough to burn fuel on contact. So what does this actually mean for you as a car buyer? Diesel engines generally give you way better fuel economy. They convert more of the fuel energy into actual power at the wheels. Some diesels approach 40% thermal efficiency compared to about 25% for gasoline engines. That means diesels waste less energy as heat and put more power to the ground. They also produce massive low-end torque. That is exactly why you see diesels in trucks, buses, and anything that needs to haul heavy loads. When you need pulling power at low speeds, diesel is king. But here is the catch, and this is important if you are shopping for a diesel vehicle. Diesel engines are built heavier and stronger because of those extreme compression forces. Thicker cylinder walls, beefier crankshafts, more robust everything. This makes them more expensive to buy and sometimes much more expensive to fix when something goes wrong. And modern diesels come with complex emission systems that need regular attention. Things like diesel particulate filters and urea injection systems. If you only drive short trips around town, a modern diesel might actually cause you more problems than it solves. More on that later. Alright, now that you understand the two main fuel types, let us talk about how engines arrange their cylinders, because the shape of your engine changes how it sounds, how it vibrates, and what kind of car it can physically fit into. The inline 4 is the most common engine configuration on the planet, and for really good reason. 4 cylinders in a straight line keeps manufacturing simple. One cylinder head, 1 or 2 camshafts, straightforward service access, lower production costs, and here is the magic. The inline 4 achieves what engineers call primary balance. The pistons are arranged so that when one goes up, another goes down. The main forces cancel out, like two equally weighted kids on opposite ends of a seesaw. Perfect balance. But there is a catch. The inline 4 has what engineers call secondary imbalance. The pistons do not accelerate at a constant rate through their stroke. This creates vibrations that show up especially at higher engine speeds. Manufacturers fix this with balance shafts. These are counter-rotating shafts that spin at twice the engine speed to cancel out those secondary vibrations. Add in quality engine mounts and good sound insulation, and modern inline 4s feel remarkably refined. But here is what excites car people. Turbocharging has completely transformed what the 4-cylinder can do. Modern turbocharged 4s produce power levels that used to require 6 or even 8 cylinders. Take the Volkswagen EA888 family or Mazda Sky Active engines. These compact 4s punch way above their weight. Now we arrive at what many consider the smoothest engine layout possible, the inline 6. And this is not just opinion, this is physics. The inline 6 achieves near-perfect primary and secondary balance naturally. No balance shafts required. The firing order and cylinder spacing cancel out vibrations almost completely. It is the engine equivalent of a perfectly balanced ceiling fan. No wobble, no vibration, just smooth rotation. The result is an engine that revs smoothly from idle all the way to redline. Refined linear power delivery that feels premium. A distinctive sound that people recognize instantly. BMW has built their entire driving identity around the straight 6. Their M20, M50, and modern B58 engines carry this legacy. Toyota and Mercedes have long histories with inline 6s as well. But here is the trade-off. The inline 6 is long, really long. Fitting it in a modern car with crash structures and crumple zones creates serious packaging challenges. It works great in rear-wheel drive cars, but in transverse front-wheel drive setups, nearly impossible. This is exactly why V6 engines exist. They give you 6 cylinders in a much shorter package. Now we are getting into the good stuff. V engines, that deep rumble when a muscle car rolls by, that high-pitched scream of a Ferrari at full throttle. Both come from V engines, but they sound completely different. Why? The answer lies in crankshaft geometry, and it changes everything about how a V engine feels and sounds. A V engine splits its cylinders into 2 banks that form a V shape when viewed from the front. This does something clever. It shortens the engine compared to an inline layout while still packing in lots of cylinders. Think of it like arranging books. You can lay 6 books flat in a long row, or you can prop them up at angles against each other and take up half the space. An inline 6 is long, really long, but a V6 fits that same cylinder count in a much shorter package. This is huge for modern cars, where engine bays are shrinking and crash safety requirements eat up space. The angle between those 2 cylinder banks matters a lot. Common angles include 60 degrees, 90 degrees, and sometimes other configurations. Each angle creates different balance characteristics and different sounds. Here is something most people do not know. V6 engines are not inherently balanced like inline 6s. Each bank is essentially a 3-cylinder, and we already talked about how 3s have balance issues. Put 2 of them together at an angle, and you create interesting vibration patterns. This is why many V6 engines use balance shafts or carefully designed crankshaft counterweights to smooth things out. A well-engineered V6 can feel almost as smooth as a straight 6. A poorly engineered one can feel busy and rough. Modern turbocharged V6 engines have become incredibly capable. They produce power levels that used to require V8s while offering better fuel economy and lower emissions. This is why luxury brands are increasingly moving to twin-turbo V6 setups. Now we reach legendary territory, the V8. This engine has defined American automotive culture for decades. If you grew up watching muscle cars running quarter miles at the drag strip, you know exactly what I am talking about. But there is more to V8s than just muscle. The engineering behind them explains a lot. Here is where it gets fascinating. There are two main types of V8 crankshafts, and they sound completely different. Crossplane cranks are what most American V8s use. The crankshaft throws are arranged at 90-degree intervals. This creates that unmistakable burbling exhaust note, that classic muscle car rumble. Think old-school Mustangs and Camaros. The uneven firing order creates uneven exhaust pulses, and that is exactly where the sound comes from. Crossplane V8s need heavy counterweights on the crankshaft to achieve smooth operation, but when properly balanced, they deliver remarkably refined power with massive torque at low engine speeds. Flat plane cranks are completely different. The throws are 180 degrees apart. This creates an even firing pattern, more like two inline fours connected together. The result? A higher revving character with a screaming exhaust note. Think Ferrari, think the Shelby GT350. That is the flat plane sound. Same cylinder count, completely different personality, all because of how the crankshaft is designed. But wait, what about even more cylinders? V10s and V12s enter exotic territory. The Lamborghini Huracan, Dodge Viper, Audi R8, these use V10s. 10 cylinders create a distinctive sound that sits between the V8 rumble and V12 smoothness. V12 engines represent the absolute pinnacle of smoothness. 12 cylinders firing in sequence create incredibly even power delivery. The firing intervals are so close together that the engine feels almost turbine smooth. Ferrari and Aston Martin have built their reputations on V12 power. But here's the reality check. More cylinders means more weight, more complexity, more fuel consumption, more expensive maintenance. And in today's world of emissions regulations and fuel economy targets, these engines face an uncertain future. Alright, we have covered inline and V layouts. Now let us get into the truly unusual stuff. This is where things get really interesting. Boxer engines, W engines, VR engines, the Rotary. Most people have never even heard of some of these. Let us fix that. First up, the Boxer. Imagine taking a V engine and spreading the banks until they are completely horizontal, 180 degrees apart. The cylinders stick out sideways instead of up or down. And here's the cool part. The pistons punch toward each other like two boxers trading jabs. Left piston goes out. Right piston goes out. They meet in the middle and retract. That is why they call it a boxer. Porsche and Subaru are the big names here. Both companies have built their entire brand identities around this configuration. So why go flat? First, the center of gravity. A flat engine sits low in the chassis, lower than an inline, lower than a V. This helps the car corner better and feel more planted. Handling improves because weight sits closer to the ground. Same principle as why sports cars sit low to the ground. Second, the balance. In a boxer layout, opposing pistons cancel out each other's forces. This creates good primary balance and a smooth running engine. The Porsche Flat 6 in particular achieves a sweet spot of smoothness and high rev capability. But here is the trade-off. Flat engines are wide. They spread out horizontally, which complicates packaging. Exhaust routing becomes tricky. Oil changes can be awkward. Accessing certain components requires more effort. Spark plug changes on a Subaru? Good luck. You will earn those skinned knuckles. For Subaru, the Flat 4 Boxer became their signature. Combined with their all-wheel drive system, it gives their cars a distinctive character. For Porsche, the Flat 6 is fundamental to their sports car identity. Now things get really complex, the W engine. A W engine is basically multiple VR banks joined together on a shared crankshaft. Volkswagen Group perfected this. Their W12 and W16 engines power some of the most exclusive cars on the planet. Bentleys, Bugattis, top-tier Audis. Why bother with such complexity? Packaging. A conventional V12 is long, really long. The W12 compresses 12 cylinders into a length not much greater than a V8. This lets manufacturers offer 12-cylinder power in cars that could not fit a traditional V12. Imagine fitting V12 power into basically the space of a V8. That is what the W configuration achieves. But this complexity comes at a cost. The crankshaft design gets complicated. You have staggered connecting rods and offset crank pins. Bearing loads become challenging. Heat management is difficult because cylinders are packed so tightly together. Service? Labor-intensive. Parts are not cheap. This is exclusive territory where buyers accept higher maintenance costs for exotic power. Speaking of VR engines, the VR6 was Volkswagen's clever solution to a specific problem. They wanted to offer 6-cylinder smoothness in cars designed for 4-cylinder mounting. Think of a VR engine as a V engine that went on a diet, a really narrow V with an angle of about 15 degrees instead of 60 or 90. This narrow angle lets all cylinders share a single cylinder head, one head covering both banks. This makes the engine compact in both length and width. The VR6 was the star, 6 cylinders in a package almost as small as an inline 4. This solved a specific problem for Volkswagen. The Golf, Corrado, and Passat all benefited from this layout. The VR6 produced a distinctive sound, sort of a smooth growl that enthusiasts recognize instantly. Now we abandon pistons entirely. The rotary engine. The rotary engine was invented by Felix Wankel. It uses a triangular rotor that spins inside an oval-shaped chamber. There are no pistons going up and down. Instead, the rotor rotates continuously, creating intake, compression, combustion, and exhaust phases through its movement. This is genuinely different engineering. Think of the difference between pedaling a bicycle up and down versus spinning a merry-go-round. Completely different motion to achieve the same goal. The rotor itself functions as the moving element, sealing against the chamber walls with what are called apex seals. These apex seals are like the rubber edge on a windshield wiper. They have to seal perfectly against the housing or you get leaks and lost compression. Mazda made the rotary famous. Their RX-7 and RX-8 brought this technology to sports cars. And in 1991, a rotary-powered Mazda 787B won the Le Mans 24-hour race outright. Not a class victory. Overall victory, the only Japanese manufacturer and only rotary engine to ever achieve that. So why is the rotary not everywhere? Apex seals. These small strips seal the rotor tips against the housing. They wear faster than piston rings in a conventional engine. Oil consumption is part of normal operation because the apex seals need lubrication. Fuel economy suffers because of the combustion chamber shape. Emissions are challenging. Unburnt hydrocarbons escape more easily, making modern emissions standards difficult to meet. But the rotary is making a comeback. Today, the best application appears to be as range extenders in hybrid vehicles. Running at a steady RPM to generate electricity eliminates many of the thermal cycling problems that cause seal wear. The rotary compactness and smooth operation make it ideal for this role. One more configuration worth mentioning: the slant engine. This is an inline engine tilted to one side. Instead of standing straight up, it leans over at an angle. Why do this? Hood clearance and center of gravity. Tilting the engine lets designers create lower hood lines for better aerodynamics. The Chrysler Slant 6 is the famous example. A tough, reliable engine that tilted about 30 degrees from vertical. Anyone who owned a 70s Plymouth or Dodge probably remembers this workhorse. Alright, we have covered cylinder arrangements. Now let us talk about how engines breathe, because this changes everything about power output. How can a 2-liter engine produce more power than a 3-liter engine? Simple. Force more air in. A naturally aspirated engine breathes on its own. No help, no forced air. Just atmospheric pressure pushing air into the cylinders when the pistons create vacuum. Think of it like running on your own lungs versus having a scuba tank strapped to your back. This is how engines worked for most of automotive history, and there is something pure about it. Natural aspiration means direct connection between your throttle input and engine response. No lag, no waiting for anything to spin up. Press the gas and power arrives immediately. The character of a naturally aspirated engine is distinctive. Power builds linearly as you rev higher. The engine encourages you to use the whole rev range. There is a reason enthusiasts love high-revving, naturally aspirated engines. That connection feels special. But here is the reality. Naturally, aspirated engines are limited by atmospheric pressure. At sea level, air pressure is about 1 bar. That is all the pressure available to push air in. Want more power? You need more displacement, bigger engines, more fuel, heavier cars, and altitude makes things worse. As you climb higher, air pressure drops. Less air enters the engine. Power drops with it. At 10,000 feet, you might be down 25 to 30% from sea level power. This is where forced induction changes everything. Turbocharging is essentially free energy, well, almost free. Here is how it works. Your engine produces exhaust gases as it runs. Those hot gases rushing out contain energy. A turbocharger captures that energy, like a water wheel capturing energy from water that was already flowing past anyway. Exhaust flows through a turbine housing spinning a turbine wheel. That turbine connects to a compressor wheel on the other end of a shaft. The compressor sucks in ambient air, compresses it, and forces that denser air into the engine. More air means you can add more fuel. More fuel plus more air means bigger explosions. Bigger explosions mean more power. A turbocharged 2-liter engine can match or exceed a naturally aspirated 3-liter engine. Same size, more power. Often better fuel economy under light loads because the engine is smaller. Modern turbos have become incredibly sophisticated. Twin scroll designs separate exhaust pulses for better turbine response. Advanced bearing systems reduce friction and improve durability. But there is a catch. Turbo lag. The turbine needs exhaust flow to spin. At low engine speeds, exhaust flow is limited. Press the throttle and you wait briefly while the turbo spools up. Then boost arrives. Modern engineering has reduced turbo lag dramatically. Some engines feel nearly instant, but the phenomenon still exists, especially under hard acceleration from low revs, like waiting for a garden hose to build pressure after you turn the spigot on. Here is an important maintenance tip that will save you money. After hard driving, let a turbocharged engine idle for a minute or two before shutting off. This allows oil to keep flowing through the turbo bearings as they cool down. Shutting off immediately can cause oil to coke in the bearings, which leads to premature failure. Think of it like letting a power tool cool down before putting it away. Turbocharging also works wonders at altitude. Because the compressor forces air in, a turbocharged engine can maintain near sea-level performance at elevations that would cripple a naturally aspirated engine. Superchargers take a different approach. Instead of using exhaust energy, a supercharger uses engine power directly. The supercharger connects to the crankshaft via a belt or gears. The engine literally drives the compressor. This means boost is available immediately. No lag whatsoever. Press the throttle and power arrives instantly. This direct mechanical connection creates a visceral, immediate response that some drivers prefer. There are different types of superchargers. Roots-type blowers use meshing lobes to push air. Twin screw designs compress air internally for better efficiency. Centrifugal superchargers look like turbos mounted on the front of the engine, but driven by belt instead of exhaust. Each type has its own character. Roots blowers create that classic muscle car whine. If you remember the blower sticking out of the hood on old hot rods, that is a Roots supercharger. Centrifugal units deliver boost that builds with RPM. Twin screws offer high efficiency and strong response. But supercharging has a trade-off, parasitic loss. Because the engine drives the supercharger, some power goes to spinning the compressor instead of reaching the wheels. At full boost, superchargers consume some of the engine output just to create that boost. It is like running your air conditioning on full blast. You get the benefit, but you lose some efficiency to power it. Turbos technically use waste energy from exhaust, making them more thermodynamically efficient. But superchargers win on response and simplicity. Intercoolers are important for both turbo and supercharged engines. Compressing air heats it up. Hot air is less dense. An intercooler removes that heat, making the charge denser and more effective. This improves both power and protects the engine from detonation. Think of it as a radiator specifically for your intake air. Cool, dense air makes more power than hot, thin air. Alright, now let us get practical. How do you keep these complex machines running? Every engine type has specific needs, but some fundamentals apply universally. Oil changes matter most. Engine oil lubricates moving parts, cools components, and carries away debris. Skip oil changes and you accelerate wear dramatically. For turbocharged engines, oil quality is even more critical. The turbo bearings run extremely hot and depend entirely on oil flow. Use the manufacturer recommended grade. Change it on schedule or earlier. For diesel owners, duty cycle matters enormously. Diesel particulate filters need to regenerate periodically. This requires sustained high exhaust temperatures. Short trips around town, never let the exhaust get hot enough. The DPF accumulates soot. Eventually it clogs. If your diesel sees mostly city driving, take it on highway runs regularly to trigger regeneration. Rotary owners have unique concerns. Apex seal condition determines engine health. Oil consumption is normal because apex seals need lubrication. Monitor compression per rotor. When compression drops significantly, the engine needs attention. Hybrid systems combine internal combustion engines with electric motors and batteries. This combination addresses some fundamental limitations of pure combustion power. Electric motors produce maximum torque from 0 RPM. This fills in the torque gap that plagues small turbocharged engines before the turbo spools up. Regenerative braking captures energy that would otherwise be lost as heat in the brake pads, like putting money back in your pocket instead of throwing it away. Alright, that covers every engine type. Thanks for watching. Like and subscribe for more. Just kidding, we are not done yet. There is one more thing I need to tell you, and this might be the most important part of this entire video. There is no perfect engine. That is the fundamental truth. Each architecture embodies trade-offs: power density versus mechanical simplicity, thermal efficiency versus emissions, maintenance demands versus initial cost. Your job is matching those trade-offs to your actual needs. Just like choosing the right tool for a job in your garage. For city commuting and short trips, small displacement inline fours, hybrids, or electric vehicles make the most sense. For long highway miles and towing, diesel remains compelling. Performance enthusiasts might prefer V-engines or boxers for their dynamic character. And finally, remember this: maintenance discipline determines outcomes more than engine choice. Any well-maintained engine will outlast a neglected one regardless of architecture. A properly cared for four-cylinder will outlive a neglected V8 every single time. But here is what most people miss. Knowing engine types is only half the battle. There is one simple maintenance habit that separates the engines that barely survive to 100,000 miles from the ones still running strong at 500,000. And almost nobody does it. I am not talking about oil changes. Everyone knows about those. This is something different, something most mechanics never mention because it takes 30 seconds and costs almost nothing. I made an entire video breaking down exactly what this habit is and why it works on every single engine type you just learned about. Inline 4s, V8s, diesels, turbos, all of them. If you want your engine to outlast everyone else's, that video is right here. Click it now before you forget. And drop a comment below telling me which engine type you are most interested in. I read every single one. See you in the next one.